When you think of NASA, you probably think of space exploration, which is a huge part of what NASA does. But what you might not know is that aeronautics, the science of flight, is also an important piece of NASA's directive. It's even in our name, National Aeronautics and Space Administration. In fact, NASA was conducting flight research long before we put a man on the moon. NASA has flown some of the world's most advanced research technologies, leading to innovations in safety, speed, and efficiency. We here at NASA's Armstrong Flight Research Center have been on the cutting edge of aeronautical development in pursuit of our goal to advance technology and science through flight. Our story began in the 1940s when the National Advisory Committee for Aeronautics, NASA's predecessor agency, teamed up with the U.S. Air Force to fly the X-1 rocket plane in pursuit of one question. Could an aircraft and its pilot fly faster than the speed of sound?
A B-29 will take the XS-1 aloft and launch her at an altitude of about 35,000 feet. The really big moment. Through the sound area. The first time ever in level flight.
They successfully answered that question in 1947. New X-planes soon followed, and throughout the 1950s, these aircraft made headlines with ever higher speed and altitude records. The fastest and most remarkable of all the rocket planes, the X-15, was flown from 1959 to 1968. There was simply nothing else like it. Pilots took it to speeds of over 4,500 miles per hour, and some flights reached altitudes so high that they passed briefly into space. Many of NASA's X-15 test pilots actually earned their astronaut wings here. One of the pilots who did not was a young man named Neil Armstrong. However, his experiences flying the X-15, as well as the Lunar Landing Research Vehicle, provided him the skills he needed on later missions, where he, of course, did end up earning his wings.
One small step for man.
Research aircraft like the X-15 provided valuable information about the human body in spaceflight and were critical in the design of future aircraft and spacecraft. The Armstrong Flight Research Center introduced the world to wingless experimental aircraft. Flown in the 1960s and 1970s, these vehicles made a great contribution to the future of spaceflight. In 1977, we applied knowledge gained from the flights of these lifting bodies when we conducted the approach and landing tests, a milestone in the development of the Space Shuttle program. The prototype orbiter Enterprise was used to verify the flying characteristics of the shuttles and to test the systems before they ever went into space. These risky flights, 5 in all, were a success, and the Space Shuttle program would go on to be one of NASA's most important achievements in space travel and exploration. During the life of the program, there were 59 successful shuttle landings here, including those of the Enterprise. Today, wingless lifting bodies are making a comeback as Sierra Nevada brings its Dream Chaser to flight status. Supporting the shuttle program was only one part of our work in the post-Apollo years. Have you ever heard the term fly-by-wire? It describes the use of electronics and computers to control an aircraft. Taking the place of mechanical or hydraulic systems, fly-by-wire technology was first tested on a modified F-8 aircraft in 1972. The flights were dangerous, but they revolutionized aviation. A fly-by-wire production system first appeared on the Air Force's F-16 and is now common on all new commercial airliners, most new business jets, and even in family automobiles as drive-by-wire systems. ABS brakes, cruise control, accelerators, even steer-by-wire, are technologies derived from research done at NASA Armstrong, and all are now part of our daily lives. Another example of aeronautical innovation NASA conducted at Armstrong is winglets, which were tested and validated here in the 1970s and 1980s. By reducing aerodynamic drag, winglets improve aircraft fuel efficiency. They are now used on all types of aircraft. We also conducted tests in the mid-70s to find ways to reduce drag on long-haul trucks with aerodynamic fairings, the results of which have also been widely adopted. As far back as the 1960s, NASA Armstrong pioneered the use of a ground control station from which to fly unmanned aerial vehicles, known as UAVs. Becoming increasingly common today, these aircraft are used by the center to develop technology that allows them to see one another and automatically take evasive action to avoid collisions. Known as Automatic Dependent Surveillance Broadcast, or ADSB, this tracking technology is something that all aircraft operating in U.S. airspace must adopt by January 2020 in order to comply with FAA regulations. Between 2007 and 2009, one of our UAVs, known as Icana, flew over thick smoke and haze to record hotspots and the progression of wildfires in California. Data from the aircraft sensors was downlinked and overlaid on Google Earth maps, then transmitted in near real time to the Interagency Fire Center, where it was made available to fire incident commanders to assist them in allocating their firefighting resources. The effects were dramatic enhancements for the fire crews. Armstrong also operates two early model Global Hawks, another type of UAV. These aircraft can fly long distances, remain airborne for up to 32 hours, and can carry large payloads of instruments into areas, such as hurricanes, that are too dangerous for scientists to fly in. NASA has long been involved in Earth science research, and the Armstrong Flight Research Center operates a variety of aircraft to support this directive, including two ER-2s, a DC-8, and a C-20, as well as the large UAVs. These aircraft are equipped with instruments that researchers use to obtain measurements of environmental phenomena, such as the thickness of ice sheets, precipitation, and air quality. Measurements and readings are often combined with global satellite observations and ground sampling to better understand these environmental conditions. In the 1990s and early 2000s, Armstrong tested hybrid propulsion technology in the hopes of making aviation greener. Other NASA aeronautical research has improved fuel efficiency, lowered noise levels, and reduced harmful emissions. But much more can be done in these areas. That's why NASA implemented the Environmentally Responsible Aviation Project to explore and document the feasibility, benefits, and technical risks that will further reduce the impact of aviation on the environment. The goal is to reduce aircraft fuel consumption, emissions, and noise simultaneously, a much more difficult challenge than working to reduce them individually. As part of this project, NASA Armstrong performed ground tests with its DC-8, measuring emissions and fuel performance of biofuels. Results indicated as much as a 50% reduction in emissions at takeoff thrust, a difference which could significantly improve the air quality around airports. And we are currently working on an adaptive compliant trailing edge flight experiment that will demonstrate a single non-rigid wing flap that can be flexed in different ways. This leads to more efficient control methods when airborne. Flying from 2007 to 2013 at Armstrong, the X-48 subscale hybrid wing body was another program in NASA's environmentally responsible aviation portfolio. NASA, Boeing Phantom Works, Cranfield Aerospace of the UK, and the Air Force Research Laboratory partnered to study the structural, aerodynamic, and operational advantages of the hybrid model, sometimes called a blended wing body. The concept is a cross between a conventional aircraft and a flying wing. The design has the potential to yield up to 30% better fuel economy than traditional aircraft due to its unique shape. The Stratospheric Observatory for Infrared Astronomy, known as SOFIA, is a partnership between NASA and the German Aerospace Center DLR. The Flying Observatory consists of a highly modified 747 SP former airliner carrying a 17 metric ton German-built infrared telescope. Missions are flown at altitudes between 39,000 and 45,000 feet, putting the telescope above 99% of the Earth's